Okay, guys, let's do electron configuration and periodic properties. This is the last section for this chapter. Atomic radii. Here I have a nice visual for you. It's nice colors. You also have one in your book, and that one actually gives the values in terms of picometers for your atomic radii. First off, how will we determine atomic radii? Well, in larger atoms like carbon or fluorine, we can actually detect the nucleus using X-ray crystallography. We can then measure the distance between the two atoms of the same type that are crystallized together, like fluorine to fluorine. We can measure that distance, and then if we measured that, that would be bond distance, but if we divide that in half, it would be the atomic radius. And so, atomic radii trends. The trend is to smaller, the atomic radius tends to be smaller as you go across from left to right, and this is caused by increasing positive charge of the nucleus. So as you go from left to right, atomic radii gets smaller. In general, as you go down a group, in the main groups, S&P blocks only, it increases, and this is due to adding another energy level, or those electrons are getting further and further from the nucleus, and so atomic radius increases. How about ionization energy? You also have a visual for this. We have it as a table on page 153, and you also have a chart like this on page 154. And it gives you the values of ionization energies. What are ionization energies? Well, it is where I take a neutral atom that is not bonded to anything, and I add energy to it to remove an electron. An ion is an atom or group of bonded atoms that has a positive or negative charge. Any process that results in the formation of an ion is referred to as ionization. In ionization energy, however, we're only interested in forming positive ions, removing an electron. And the energy that is required to remove the first electron from a neutral atom of an element is the ionization energy, or the first ionization energy. So, in general, the ionization energy of the main group elements increases from left to right. This is caused by increasing nuclear charge. It's going to get more and more difficult to pull off that electron. There are exceptions, and we'll talk about those in class and which ones I expect you to remember. In each group or column of the periodic table, ionization energy decreases and down a group, and this is due to increasing number of energy levels and that makes the outer electrons further and further from the nucleus, which then causes the electrons to be easier to remove, therefore reducing the ionization energy. However, what if I take off a second or a third electron? In this chart, as in the chart in your book on page 154 or 155, you can see that there are ionization energies listed for sodium, etc., and they are going from 1 electron to 2 to 3 to 4. And we see if we go from the first ionization to the second, it's almost a 10 times increase from sodium. But when we do magnesium between the first and the second, it's only double. But then when we go from the second to the third electron being removed, it now is almost 5 times as great. Why is there this big gap? And you see it kind of stair steps down. That's because this is a valence electron, but this is a core electron. When I remove a valence electron, it's difficult, yes, but not nearly as difficult as removing a core electron. And that's also true for magnesium. So when we see these large increases, we know we've gone from a valence electron to a core electron in each and every case. So, large increases, you're now removing core electrons. Electron affinity is actually forming a negative ion. We had to give it a different name, and so we call it electron affinity. And it's the energy change that occurs when an electron is acquired by a neutral atom. If this energy is a product, if I have energy given off in this process, then that energy would be negative. If the energy is positive, it would actually be a reactant. But those are pretty unstable, and so we don't see those a lot. Here are some electron affinity charts. Again, aren't you surprised? But you have these in your book. You have it on the periodic table on page 157, and you have it in a plot similar to this one on page 158. And so here, unlike your book, we have these positive, these numbers are kind of reversed as to what we would think. This is more and more negative, meaning it's more and more favorable to add an electron to these elements. Your book, they reverse it, and so I kind of think of it this way more, so whichever way works for you is fine. It's more negative to add an electron to fluorine than it is to, say, oxygen or beryllium, because that would actually complete the octet for fluorine, so it makes it into a very stable ion. So, electron affinity trends. Electron affinity increases until we reach the halogen group in any period, and groups tend to decrease. The groups tend to decrease in electron affinity as you go down due to decreased effective nuclear charge and due to increased atomic radius. So this time our nuclear charge is smaller because we have so many electrons already on there. We've got a lot of protons, but we also have a lot of electrons, and they are further from the nucleus, so that makes the ionization or the electron affinity even lower. Whenever we add a second electron, those energies are always positive. Ionic radii. Cations are positively charged ions, and they get smaller because now I have more protons than electrons, and so they always get smaller. Anions are negatively charged, and so they always get bigger because now I have more electrons than protons, so it's harder to hold them close. Here is a picture of one of those. And you'll see on here we have the atomic radius and we have the ionic radius listed. The orange would be the atomic and the ionic is listed below it, as are they listed over on the other side. They've just used different colors where they have the atom, and then you can see the anion gets much larger. But still, as we go across, they tend to get smaller, and then when we hit the anions, they're much larger, but then that group, they tend to get smaller again as well. So, anions are always larger than cations, and as you go from left to right, cations get smaller, and the anions get smaller. If you go down a group, anions or cations all get larger. Valence electrons increase from left to right for the main group elements 1 through 8, or 1 and 2, and then if you count 13 through 18 depending on your periodic table, we go from 1 to 8 electrons. Electronegativity. Electronegativity is a measure of the ability of an atom in a chemical bond to attract electrons from another atom in a compound. Electronegativities increase from left to right and from top to bottom. So the most electronegative element would be fluorine. These are always measured relative to something else, and so to measure these they set fluorine at 4.0 and then measured everything relative to fluorine. And that table listed in your book is on page 161. You'll need it for the homework. Periodic properties of D and F block. I'm going to ask you to read that in your book. It's only about 1 page worth of reading, so I think you can manage that. So, vocab, go to page 165 in your book, and you need to know them all. Okay, thanks.